We have a presentation today from Kirk Sorensen, founder of Flibe Energy. Kirk has been a promoter of energy from thorium for a long time. He has a website, energyfromthorium.com, where a pretty big community of amateurs and experts from around the world have been contributing to the community effort to define what would be the optimal thorium reactor, nuclear reactor that generates electricity from thorium. This is a technology that's been around for a long time, since shortly after World War II. It was matured well up until early 1970s, and then kind of suddenly ended in favor of the liquid metal fast breeder reactor, which then also ended. And Kirk's going to give us a talk today and explain kind of what went wrong, why it stopped, why it hasn't been done. You know, if it's such a great idea, why aren't we doing it? And there are actually some very good reasons for that, and many of those reasons are past, and maybe we should start doing it again. So please, Kirk Sorensen.
Thank you very much, Chris. I'm very glad to be here at Google today and giving another tech talk. I always enjoy coming and being a part of these things. The question that I'm going to try to answer today is one that I'm often asked as I give presentations on thorium. In fact, I'm almost always asked this question, which is, Kirk, thorium sounds like a great idea. It sounds like it's a good technology. Why didn't this happen? We are, Flibe Energy, a new company to develop liquid fluoride thorium reactor technology. We're following the vision of Alvin Weinberg. He was the director of Oak Ridge National Labs from the 50s to the 1970s, and he had a vision of how we could use thorium to advance beyond the current constraints of our society in terms of fossil fuels, hydropower, and existing nuclear technology. One of the amazing parts about his vision was how this could transform not only the U.S. economy, but many other places in the world, some of which don't have the resources that we have in terms of fresh water or arable land. This is a vision he had of how thorium reactors could be used to desalinate water, grow crops in desert areas, and to, some of us like to call it terraforming the earth, but to really truly change the economic balance of the world. Weinberg's vision, on the other hand, was brought to an end in the early 1970s, and that really is the subject of the talk today. There really were three options for nuclear energy at the dawn of the nuclear era. There was uranium-235, which was the fissile form of uranium. This was the form of uranium that could actually be utilized directly in a nuclear reactor. Most of the uranium was uranium-238. This had to be transformed into another nuclear fuel called plutonium before it could be used. And then there was thorium, and in a similar manner to uranium-238, it also had to be transformed into another nuclear fuel, uranium-233, before it could be used in a reactor. There were some significant differences, though, between these three fuels. As I mentioned, uranium-235 could be used directly. The other two had to be transformed, and that meant they needed two neutrons to be consumed, one to transform them and one to fission them. And in order for this to be a sustainable process, you had to know, well, will they emit more than two neutrons when they fission? And the answer was, yes, they did. In fact, all three of them emitted more than two neutrons when they fissioned. Here was uranium-235. Uranium-233 emitted about 2.5 neutrons per fission. And plutonium would fission with almost 3 neutrons per fission. So it would emit the most neutrons when it fissioned. So the first answer was yes. All three of the fuels gave off enough neutrons to sustain their consumption in a reactor. But there was more to the story. This is a busy graph, and I apologize in advance for it, but it tells the story of much of our nuclear history. And what it shows is plutonium doesn't emit enough neutrons when it isn't being fissioned by fast neutrons in order to continue the conversion of future uranium into plutonium, continue its breeding. It has to be fissioned by fast neutrons in order to do this. On the other hand, thorium and uranium-233 produce enough neutrons in both thermal and fast fission to continue the utilization of that fuel. I call it the threshold of 2. And it's not just about how many neutrons they emit, but how many neutrons they emit, even accounting for absorption. Because they don't always fission every single time they're hit by a neutron. Uranium-233 and plutonium-239, of those two in thermal neutrons, only uranium-233 crosses the threshold of 2. In fast fission, on the other hand, both uranium-233 and plutonium-239 cross the threshold of 2. So it would seem, well, we just want a fast reactor. We don't want a reactor that uses slowed down thermal neutrons. We want a fast reactor because then we will have great confidence that we will be able to sustain the consumption of nuclear fuel. Well, there's a powerful disincentive to doing it this way, and it has to do with what are called cross-sections. These are a mathematical way of describing how likely it is that a nuclear reaction will proceed. And they take the form of areas, quite literally an area, sometimes called a barn, which is 10 to the minus 24 square centimeters. This is a really, really, really small unit of area, but this is the unit that nuclear engineers use to describe how probable a nuclear reaction is. This is the cross-section of uranium-233 to a thermal neutron. By comparison, this very, very small circle right here is the cross-section of uranium-233 to a fast neutron. So it's not hard to see which one is more likely to have a fission reaction. A thermal neutron is far more likely to cause a fission reaction than a fast neutron. So the advantage now seems to be for the thermal reactors. This is a general feature of almost all nuclear materials, that their cross-sections are much larger to thermal neutrons than they are to fast neutrons. Here we see the cross-section of plutonium. It's huge in the thermal spectrum, and it's very, very small in the fast spectrum. And that means that plutonium is much more likely to have a nuclear reaction to a slowed-down neutron than to a fast neutron. So again, why consider a fast reactor? Well, it's because look at these red regions. Those red regions indicate the probability that the neutron will be absorbed but not cause a fission, that it will simply just be absorbed. You can see that that probability is about 10% for uranium-233 in the thermal. But if we were to magnify that cross-section significantly by a factor of 500, you could see that that probability becomes much smaller in the fast spectrum. A fast neutron, if it is absorbed, almost always will cause a fission. This is significant for uranium-233, but it's much more significant for plutonium-239. It will absorb a neutron about 1/3 of the time and not cause a fission. But in the fast spectrum, it will almost always cause a fission. So to make sure that we cross that threshold of 2, it was necessary to build fast reactors that would use plutonium. On the other hand, it was conceivable that you could build thermal or fast reactors that would use uranium-233. This uncertainty was not particularly appealing at the time. They wanted to move out in directions that they felt very confident about. And so the United States began to pursue a fast breeder reactor. In 1951, they built the experimental breeder reactor 1 in Idaho. This was a fast breeder reactor. This was a reactor that was going to not slow down neutrons, but use fast neutrons to convert uranium into plutonium and to breed from it. This was actually the first reactor to generate some power. It lit 4 little light bulbs and ultimately generated, I believe, several hundred kilowatts of power. But it shows how early the United States was moving out on the fast breeder reactor. It was followed by the experimental breeder reactor number 2, which was also a fast breeder reactor, much larger this time. It made 62 megawatts of thermal power. Industry got excited about the potential for making breeder reactors. This was actually a commercial reactor, the Enrico Fermi breeder reactor in Monroe, Michigan. They began working on this reactor in 1957, and it achieved criticality in 1966. But shortly after it achieved criticality, they had a small meltdown at the Enrico Fermi reactor where the reactor was damaged and shut down. At this time, Alvin Weinberg and his colleagues at the Oak Ridge National Labs were working on molten salt reactors. These were reactors that didn't operate in the fast spectrum. They operated with slowed down neutrons, and they predominantly were interested in using thorium and uranium-233. Weinberg wrote an introduction to a series of papers that were published in a nuclear journal in 1969, and these are some of the words that he used. And I've always found it very interesting how careful and measured he was with his utilization of language, because he knew that most of the effort in the country was on the fast breeder reactor and very little in comparison was on the molten salt reactor. He said, "The prevailing view holds that the liquid metal fast breeder reactor is the proper path to ubiquitous permanent energy. It is no secret that I, as well as many of my colleagues at Oak Ridge, have always felt differently. When the idea of the breeder was first suggested in 1943, the rapid and efficient recycle of the partially spent core was regarded as the main problem. Nothing that has happened in the ensuing quarter century has fundamentally changed this." So Weinberg begins to lay out the scenario that physics hasn't changed And unless you can rapidly reprocess nuclear fuel, you won't be able to realize the benefits of the breeder reactor. He then goes on to offer an alternative to the prevailing view. The successful breeder will be the one that can deal with the spent fuel or the spent core most rationally, either by achieving extremely long burnup or by greatly simplifying the entire recycle step. We at Oak Ridge have always been intrigued by this latter possibility. It explains our long commitment to liquid-fueled reactors, first the aqueous homogeneous and now the molten salt. So he presented a different scenario, how they could use fluid-fueled reactors to achieve the overall goal of the efficient utilization of nuclear fuel. And the series of papers that followed in this were some of the first discussions in the nuclear literature about the potential of the molten salt reactor. It was not well known. The monies that had been appropriated in order to research the different breeder reactor types are listed in this graph. And I found this graph thanks to a book that had been scanned into Google Books, thanks to a project started by my good friend Chris Ulick here. So I greatly appreciate this. Is one of the many things I'm sure people have done with your work. Numbers are one thing, so I took it and threw it in a spreadsheet and made a nice graph. The red line shows the expenditures on the fast breeder reactor. And this graph only begins in 1968. At that point, the United States had already built several fast breeder reactors. We're looking at $75 to nearly $100 million in 1968. It's very hard to see the green line for the molten salt breeder reactor technology. It's extremely low. And then ultimately it was canceled and briefly resurrected in 1975 and then canceled again. On the scale of the appropriations that were made to the fast breeder reactor, you just about can't see the appropriations that were made to the molten salt breeder reactor. In June of 1971, President Richard Nixon made a speech where he talked about the need for the fast breeder reactor. He put the United States on record that this would be a top national goal. Now, we don't have any video from the speech he gave that day, but later on in that day, he called Representative Craig Hosmer from California to tell him about the speech about the breeder reactor.
Yeah.
Congressman Craig Hosmer, sir. Ready?
Hello, Mr. President. Since you missed our meeting when we had on breeder reactor, you know, I wanted you to know that we sent the message today, Craig, but that I just told Ziegler to tell the press that it's a bipartisan effort that you and Hollifield and so forth had been bugging me about it. The one thing I wanted to tell you too is that Hollifield was there last night for the 8 Club thing, and I've told the people around here, now this has got to be something we play very close to the vest. But I am being ruthless on one thing. Any activities that we possibly can should be placed in Southern California in this field and also in the saline water field. Good. You know, we need the jobs. We need to sop up those aircraft workers. Now, we're going to do a couple of new things on water, for example, and I've decided to throw one big plant into Southern California. I mean, you know, a big, one of these implementing, you know what I mean, it's just a question of how big the plant is. But in this energy field, I've told Dr. David and of course Seaborg and the rest that we do it. So on the committee, every time you have a chance, needle them, say, where's this going to be? Let's push the California thing. You do that?
Incidentally, Mr. President, I am so delighted you released that $16 million on the improvement of the enriching complex.
Good.
That handles a bad blood problem for us.
Right. Good.
Unplug some.
Well, they told me you were interested in it, and I said, well, if Hosmer's for it, I'm for it.
All right, let's pause there. You can tell just a little bit from listening to Nixon's words that the fast breeder reactor was viewed by him and probably some others in his administration as something that they could use to economic advantage for the people of Southern California. To get it, Nixon was from California, Hosmer was from Southern California, Chet Holofield, who ran the Joint Committee on Atomic Energy, was also from California. And I think some of the phrases in this phone call are very interesting. I'm going to be ruthless on this. We've got to play this very close to the vest. It's about jobs. If you're for it, I'm for it. It doesn't lead me to believe that the president was seriously considering alternatives to the fast breeder reactor and other paths that could be taken. It was a focus on what can we do right now to get jobs back home to the folks who are going to support us in re-election. Well, a few months later, Nixon was at Hanford, Washington, which is the site of many of our nation's earliest nuclear energy facilities. And he was also giving a talk on the significance of the breeder reactor. And again, note the economic potential that he puts in front of people during this talk.
That is why I made an announcement on June the 4th, one that didn't get, of course, the enormous publicity of the announcement of the journey to China, one that didn't get the publicity of my announcement of the new economic policy to deal with the problems of inflation and unemployment in this country, but one which, in terms of the future of the country, may be in long-range terms, even more important in some respects. And that is that the United States was going to go forward in building a breeder reactor. Now, don't ask me what a breeder reactor is. Ask Dr. Schlesinger, but don't tell him not to tell you, because unless you're one of those PhDs, you won't understand it either. But what I do know is this, that here we have the potentiality of a whole new breakthrough in the development of power for peace. And that means jobs for this area, but jobs and power for hundreds, for millions of people all over the world.
Jobs is what it was all about. And this area that Nixon was talking to in Hanford, Washington, this was a very well-educated area. A lot of the people in the background there probably had PhDs in nuclear engineering and knew exactly what a breeder reactor was. But Nixon was emphasizing the economic benefits to them of his announcement that there was going to be a breeder reactor.
All of this business about breeder reactors and nuclear energy and the stuff is over my head. That was one of my poorest subjects, science, and I got through it, but I had to work too hard. I gave it up when I was about a sophomore.
Well, maybe it might have benefited our country a little more if Nixon had been able to ascertain the different values of different types of breeder reactors and why one might have an advantage over another. But nevertheless, the U.S. was now firmly on the course of making the breeder reactor a national priority. Nixon emphasized it in his State of the Union speech. He then emphasized it in another message to Congress. The Democratic and Republican Party platforms in 1972 both included the fast breeder reactor as a national priority. Now, this is about the time when Weinberg's story with the molten salt reactor begins to intersect this much larger story of the breeder reactor and the congressional support behind it, as well as the presidential support. Testimony given in September of 1972, they noted that the U.S. government would be expected to cover cost overruns on the breeder reactor, and the development cost would go over $700 million. At this point, industry had already committed $200 million, these are then-year dollars, to the breeder reactor effort. Representative Craig Hosmer, who was the fellow on the phone call that we heard earlier, said that if cost targets were missed, I, for one, don't intend to scream and holler about it. It's not hard to see that they could see great economic benefits accruing to their area of the country if the breeder reactor program was to go forward. In that same month, the Atomic Energy Commission issued WASH 1222, which was an evaluation of Weinberg's molten salt breeder reactor. It was highly critical of several technological issues that had been encountered during the development of that idea. More importantly, though, it almost completely ignored the safety and economic improvements possible through the use of the molten salt breeder reactor technology. Weinberg himself had a meeting with Chet Holofield and Milton Shaw of the Atomic Energy Commission in 1972. We don't know exactly when this meeting took place. Our only record of it is contained in Weinberg's book, his autobiography, The First Nuclear Era. Here's what he said. I found myself increasingly at odds with the reactor division of the Atomic Energy Commission. The director at the time was Milt Shaw. Milt was cut from the Rickover cloth. He had a singleness of purpose and was prepared to bend rules and regulations in achievement of his goal. Why would he feel this pressure if he has the president and these congressional folks pushing for the fast breeder reactor? At the time he became director, the Atomic Energy Commission had made the liquid metal fast breeder reactor the primary goal of its reactor program. Milt tackled the LMFBR project with Rickoverian dedication. Woe unto any who stood in his way. This caused problems for me since I was still espousing the molten salt breeder. Milt was like a bull. He enjoyed congressional confidence, so his position in the AEC was unassailable. And it was clear that he had little confidence in me or Oak Ridge. After all, we were pushing molten salt, not the fast breeder. More than that, we were being troublesome over the question of reactor safety. And that was another aspect that was getting Weinberg into trouble. He had invented the pressurized light water reactor that formed the backbone of the reactor technologies that were being developed in the country at that time. Here's a picture of some of the pressurized water reactors. His work on the thorium reactor led him to believe that a significantly higher level of safety was possible. And this, in large part, was because the thorium reactor operated at low pressures. whereas water-cooled reactors operated at high pressures. So he was beginning to bring these issues up in support of the thorium reactor. But it didn't have that effect. Congressman Chet Holofield was clearly exasperated with me, and he finally blurted out, "Alvin, if you're so concerned about the safety of reactors, then I think it might be time for you to leave nuclear energy." But I was speechless. But it was apparent to me that my style, my attitude, and my perception of the future were no longer in tune with the powers within the AEC. And I think this was a very sad moment in the history of our country and probably in the history of the world, because an entire direction of potential development was being ended at that moment by a not well thought out comment by Congressman Holofield, who was very powerful. Weinberg looked at this fairly philosophically when he wrote his autobiography in 1994. He said, "I look back on these events, I realized that leaving Oak Ridge was the best thing that could have happened to me. My views about nuclear energy were at variance with those of the AEC and congressional leadership. After all, it was I who had called nuclear energy a Faustian bargain, who continued to promote the molten salt breeder." So Weinberg's pursuit of thorium appears to have had a great deal to do with why he was fired from his position at Oak Ridge in the Atomic Energy Commission. And it's not hard to see, when you stack up the forces that were in support of the fast breeder and that effort, the money, the industrial backing, the confidence they had, and here is Weinberg trying to push something different, why they would attempt to truncate his work. The upshot of that was, in January of 1973, Oak Ridge was directed by the Atomic Energy Commission to terminate the development of the molten salt reactor. April of that year, Nixon went on to reiterate his commitment to the fast breeder, saying it would extract 30 times more energy from uranium than light water reactors, and it was the highest priority target for nuclear research and development. We weren't the only ones pursuing the fast breeder reactor. In August 1973, the Phoenix reactor in France achieved criticality. So we had real competition in this area, and I think it had something to do with the zeal the United States felt to become preeminent in this field. But then something else happened in 1973 that was far more significant. The Yom Kippur War started. It led to the OPEC oil embargo. Suddenly, the United States, their supply of oil was cut back tremendously. There were long lines at gas stations. People were having to alternate days when they could buy gas. People were sometimes not able to get to work. An enormous amount of economic activity was truncated. Nixon felt great pressure, so he announced Project Independence, which was a plan to make the United States energy independent by 1980. This involved building many fast breeder reactors, many conventional reactors, new oil drilling, new refineries, new coal mines, all kinds of things to make the United States independent in energy supply. He promoted these in talks before Congress, but then in March of 1974, the oil embargo ended, and pressure reduced to implement Project Independence. But something else happened that was very significant in 1974. India detonated a nuclear weapon that had been built from plutonium separated from natural uranium in a heavy water reactor. This was a very significant event in the history of how the United States approached nuclear power, because they became quite fearful that plutonium that could be separated from uranium in reprocessing facilities would be able to be used in a nuclear weapon. And there are many arguments why that is not feasible in conventional light water nuclear reactors, but there are also other arguments in how changes in how you would put fuel through a reactor could lead to so-called weapons-grade plutonium rather than what we call reactor-grade plutonium, which is not suitable for nuclear weapons. The entire fast breeder program was partially built on the assumption that separated plutonium would be available from the light water reactors that we had already built. If we were able to take that plutonium out, we would be able to start these fast breeder reactors, because they required significantly more nuclear fuel to turn them on than a light water reactor did. And that had to do with those relative cross sections I showed. How big the plutonium cross section was in the thermal reactor versus how small it was in the fast reactor. That's why it takes so much more fuel to start a fast breeder reactor for the same electrical power rating than a thermal reactor. Nixon resigned in 1974 and Gerald Ford became the president. He put some changes in place for the Atomic Energy Commission, splitting it into two new divisions, the Nuclear Regulatory Commission and the Energy Research and Development Administration, which would go on to become the DOE. The Joint Congressional Committee on Atomic Energy, led by Chet Holofield, was abolished. The balance of power was changed when Ford came in 1974 and made these changes to the AEC and to the Congressional Committee. But Ford still supported the fast breeder reactor. He mentioned it in several of his speeches, including in the State of the Union address. He increased funding for R&D for the fast breeder reactor. And he highlighted how the fast breeder reactor could be used to extend uranium resources for centuries. As the 1976 election approached, though, it was very close between Jimmy Carter and Gerald Ford. Jimmy Carter wanted uranium reprocessing to be abolished. He did not want it to take place. Only about a week before the election, on October 28, 1976, Ford took Carter's position. He said, we are not going to reprocess uranium anymore. We're not going to separate plutonium. And he highlighted the risk of proliferation as one of the main reasons why he was making this decision. But it's almost certain that pressure from Carter and an attempt to improve his potential to win the 1976 election had to have something to do with it. At that time, the proposal was to build another fast breeder reactor, this time in Tennessee, very close to Oak Ridge, on the Clinch River. So this was the proposal that was before the nation as Jimmy Carter became the president in 1977. And Carter was not a supporter of this fast breeder reactor. He considered that the fast breeder reactor and its concentration had had something to do with the lack of technology development in solar energy. He blamed the focus that had been on the fast breeder reactor. He called our society a plutonium society that would use the fast breeder reactor. In April, he reiterated Ford's ban on reprocessing. So, not too much of a surprise, Ford had basically assumed Carter's position. Carter says, yes, we will continue that as national policy. He also called for a cutback in funding for the Clinch River breeder reactor, however. He announced a new energy plan focused less on petroleum and more on coal. He said there's no need to enter the plutonium age by licensing or building a fast breeder reactor, such as the proposed demonstration plant at Clinch River. And again, he blamed the emphasis on the breeder reactor for slow progress made in the progress of solar power. Surprisingly, Carter knew a thing or two about thorium. And the reason he did is because at this time, Admiral Rickover was working with his Naval Reactors branch to load a thorium dioxide, uranium-233 dioxide core into the shipping port reactor. Carter was able to turn the switch that turned the first and only thorium breeder reactor in U.S. history on. Several times he mentioned how we wanted to try other approaches to breeder reactors than plutonium, specifically light water breeder reactors using uranium. But then a meltdown happened at 3 Mile Island. Public confidence in nuclear energy, and particularly in the light water reactor, really went down. Even after Ronald Reagan was elected and lifted the ban on commercial reprocessing, no reprocessing plants were built. In 1982, the shipping port reactor, which had been running for 5 years at this point on a thorium uranium-233 core, was shut down. And when they examined the fuel, they found that there was 1% more fuel in the reactor than there was when they started. This proved, finally, a thorium breeder reactor was possible in a thermal spectrum. It had actually been done. It wasn't a thorium molten-salt reactor, but it was a true thorium breeder reactor. Another consequence of the decision not to reprocess nuclear fuel meant that we had to have a new strategy for the long-term disposal of plutonium. Previously, it had been assumed that plutonium from light water reactors would be sent to fast breeder reactors, but without that, we needed to know what to do. And so President Reagan signed into law the Nuclear Waste Policy Act, which continues to be the law of the land to this day and led to things like the Yucca Mountain Repository. The funding that went into the fast breeder reactor surprisingly peaked even after the United States had made a decision not to continue with reprocessing. And even under the Carter years, from 1976 to 1980, you can see funding levels for the fast breeder were very high. So this was a reactor type that dominated the long-range planning of the United States for many, many years. The Atomic Energy Commission saw plutonium as a sure bet in the fast breeder. It could cross the threshold of 2. There wasn't uncertainty there. There was a degree of uncertainty with thorium. They invested early and heavily in the fast breeder reactor despite failures and meltdowns. And industry got involved with hundreds of millions of dollars of investment. In 1971, Nixon made this the U.S. strategy. How we were going to go forward was going to be based around the fast breeder. And shortly thereafter, Weinberg was fired and the molten salt reactor program was canceled. But Ford canceled the fuel processing program and Carter extended that ban. Without fuel reprocessing, the fast breeder was not a viable candidate anymore. And nobody, as far as we know, in DC ever revisited the question of was it a mistake to cancel the molten salt reactor effort? Should we have gone back and said, you know, now that we're not going to do the fast breeder, maybe we should have done the molten salt breeder reactor? In all of my studies, I have not been able to find any indication that that ever took place, that there was a true revisiting of that decision to shut down and a rethinking. The team that worked on this at Oak Ridge disbanded and dispersed, and over the decades that followed, the knowledge was slowly forgotten. So now, here we are in 2011, asking, why is now the right time for the liquid fluoride thorium reactor, which is the modern form of the thorium molten salt reactor originally proposed? We know that we need much more energy at much lower prices, and we have to do this with a much lower impact on the Earth's environment. We know that we're facing severe challenges from global climate change, melting of glaciers, rising sea levels, changing weather patterns. We need to reduce the amount of carbon dioxide we're putting into the atmosphere dramatically. There's tremendous uncertainty amongst the public about nuclear power because of the events at Fukushima Daiichi. Even though no one was killed there, the coverage and the tone that it took has made people question the safety of nuclear power, primarily the light water reactor. To be able to have a different technology that doesn't have some of the risks of operating high pressure fluids and reactors that have the capability to have meltdowns is significant. Our alternatives in the form of fossil fuel cause tremendous environmental degradation, not just in mining and processing, but also to our atmosphere, transporting these fuels. It's not cheap to build electrical power transmission lines either. So even if we wanted to build renewable energy sources dispersed in a wide variety of places, they would face challenges in order to get transmission lines built from here to there. To give you an idea of just some of the things we do in our high-tech online society today, this is a picture of a data center for Facebook that has been built just 100 miles south of the Arctic Circle in Sweden. It consumes 120 megawatts of hydropower. Has 14 backup diesel generators to provide 40 megawatts of emergency power. It costs $760 million. This is one of the largest solar installations in the world. It's sited on 185 hectares of land. It provides 20 megawatts of peak energy for 15 hours a day at $420 million, or about $33 a watt. That's 6 to 7 times what it costs to put other power transmission in. So this is in Spain, and the data center is in Sweden. So here's an example of a customer that has a dense power demand. It wants continuous power, no interruptions, and it's in frozen Sweden. And here's a diffuse power supply in Spain. So to run this building off those solar power systems, we'll need at least 6, but we need more because these plants can only provide power for 15 hours a day. So we'll need probably 10 or more of these sites to run one of these data centers. Plus we'll need intercontinental transmission lines to get power from a place like Spain that's nice and sunny to a place like Sweden that's frozen. Is this what's going to happen? Probably not. Probably what will happen is something more like this, where a dense power supply in the form of coal. This is the prettiest coal plant I've ever seen in my life. This is in Germany. But it provides 1,600 megawatts of continuous power by burning lignite coal. Look at that. We could run 13 of those data centers with one of these coal plants. Sounds great, right? Well, unless you're the environment. If we try to use expensive, intermittent, and alternative energy, that's not going to be the answer. Most populations, most people on Earth can't afford unsubsidized alternative energy. It's just too expensive. What they'll go towards is cheap, reliable, dirty energy. That's not a viable answer for the world either, but it's the one that will be taken because most people don't have alternatives. We believe natural, inexpensive, and abundant thorium is the answer. This is the material that is dense enough and reliable enough to provide the energy that the world needs. But the machine to make it work is the key. Why molten salt? Because molten salt is the only one of the 4 potential coolants in a reactor that can run at both high temperature and low pressure. It also has a remarkable feature because of the properties of molten salt. In the event of an emergency, the fuel can be drained into a passively safe, passively cooled configuration. This is something that you can't do with a solid-fueled reactor. Finally, the advantages of the molten salt reactor are significant. Inherent passive safety through having fluid fuel and operating at low pressure. You can operate at high temperature, which means you can get high thermodynamic efficiencies. Your fuel preparation costs are very low, and there's no fuel fabrication costs. Fluorides also turn out to be an excellent chemistry match with the uranium-thorium fuel cycle. They're chemically stable and they're impervious to radiation damage. That enables us to achieve unlimited fuel burnup and continuous recycling of the material from core to blanket. Uranium-233 is highly unsuitable for weapons diversion because of contamination with uranium-232, and it's easy to downblend it in emergency. Now, we do have challenges. These salts can be aggressive towards most metals and structural materials. It requires special materials to avoid being corroded by the salt. High temperature operation is also both a blessing and a challenge. But I think the fact that the technology base has largely stagnated for 40 years is our single greatest challenge towards going forward. And also the unknown nature of this within the nuclear community. It's very different than what we do today with water-cooled, uranium-fueled reactors. They are the basis for today's regulatory environment. And so there will be a great deal of education needed for this technology to go forward. But I think it has great potential because of these attributes. And Flibe Energy aspires to be the world leader in the design, development, and manufacture of these liquid fluoride thorium reactors. Thank you very much.